So this is lesson 16 out of 28 in our semester. I think I'm going to spend the day going over the homework assignment, which was a few problems from the Farlow book and 10 problems in the first section of the Logan book. Are there any questions before I start?
Yes, good morning, Professor.
Good morning.
From the homework number 7, can you do the number 4 from page 41?
I will take a look. Let me see. Okay, so this is in Farlow, page 41, but you can't do number 4 without using number 3. So I will have to start with number 3. And number 3 is to compute the Fourier expansion of the very simple function phi of x equal 1 for x between 0 and 1 using the Fourier sine expansion. So we have the formula for the Fourier coefficients. So for the sine expansion, the Fourier coefficient a sub n is 2 times the integral from 0 to 1 of whatever is my function phi of x sine of n pi x dx. But in this case, it's a little bit easier because phi of x is equal to 1. And and when you have the Fourier coefficients, phi of x is the sum from 1 to infinity of a sub n sine n pi x. So for the expansion of a function in terms of sines, that is the basic formula. So we only have to compute this for n equal 1, 2, and 3. Or 4. Let's do it for 4. So a1 is 2 times the integral from 0 to 1 of sine. Well, actually, we can just do this in general because it's quite easy. So this is the formula for an. And when you integrate sine of n pi x, you get minus 1 over n pi cosine of n pi x, evaluated from x equals 0 to x equal 1. Now, if n is even, n pi x, well, this is automatically equal to 0, equal to 1. The cosine of 0 is 1. And if n is even, then n pi, when x is 1, this is n pi. N pi is, so this is minus 1 over n pi. What is cosine of n pi? It's -1 to the n. It's 1 if n is even, and -1 is n if n is odd, -1. So if n is even, these cancel. And if n is odd, so this equals 0 if n is even. And if n is odd, this is -1 minus 1 is -2, 2 over n pi for n odd. Right. Does that look okay?
Oh, yes.
All right. So let's see. Oh, sorry. There's a 2 here. I forgot the 2. 2, 2, 4. So what we get is 1. So phi of x is 1. The summation, what is an? 4 over n pi. 4 over pi sine of n pi x over n, and goes from 1 to infinity through the odd numbers. And draw the first 3 or 4 terms. So I'm actually going to see if I can do this using Maple. So hopefully this will be possible. Let me try share screen. And let me cancel that. Let me try something else. Okay, can you see this Maple screen?
Yeah.
Okay, so suppose I define the following function. Four over pi times sine of pi x over 1. And if I plot f of x, x going from 0 to 1, oh, sorry, sine of pi times x, that's my function. Ah, okay. So if I take the first term of the Fourier series, that's what it looks like. And let me always compare this to the constant function 1. So this is the constant function 1, and this is the first term of the Fourier series. Then we add another term, plus sine of 3 pi x over 3. So this is the first two terms of the Fourier series. Oops. Oops, it should be a capital P. So this is what the first three terms look like. It's getting a little bit closer to the constant function 1. Let's do another one. We're only adding the odd integers. So I want to change this to 5. Oh. Okay, so this is the function. And now if I plot it, it is getting a little bit closer to this, right? Let's try a fourth term. So this is 7. Getting a little bit, so it's not 1, but it's getting closer. So this is the Fourier series. Let's do it more generally. Let's see if I can do it like this. Suppose I want to make a sum of, oops, two k minus 1 times pi over 2k minus 1. You see, what I had here is the first 4 terms. So k goes from 1 to 4. So this should be exactly the same. Oops. Let's see now. Yeah, so this should be exactly the same plot. Yeah, there it is. So suppose instead of 4 terms, let me go to 7 terms. Ooh. Let me go to 10 terms. Yeah. Let me go to 100 terms. Oh, wow. That's what the graph of the first 100 terms of this Fourier series looks like. I mean, it's getting pretty close to 1. I mean, you can't do this by hand. That's why God invented computers. If you take the first 500 terms of the Fourier series, that looks to me pretty much like the constant function 1. It's a little bit of problems here at the endpoints of the interval, but that's exactly what's going on. So,
Professor,
yeah.
what about the Taylor polynomials? Is very similar to the Fourier series.
Well, the Taylor polynomials give you a polynomials. What we have here are some of trigonometry. Here we're not adding powers of x, we're adding trigonometric functions. So there are a lot of similarities, perhaps, between Fourier series and Taylor series, but they are quite different. Okay, stop share. So now we should be back here. So, so in problem 3, when it said draw the first 3 or 4 terms, I just drew the first 3 or 4 terms, and then I drew the first 500 terms. So what is the solution of the initial boundary value problem? So when we solve when we do our separation of variables, we get solutions u sub n of xt, which is a sub n. So this is now part 4. And our differential equation, our diffusion equation or heat equation is u sub t equals u sub xx, x between 0 and 1. So the alpha in this case is 1 because it's u sub t normally equals alpha squared uxx. And in this case, alpha is 1. And so we have u sub n of xt is a n e to the minus n pi alpha, but alpha is 1, squared t sine of n pi x. And what is an? An is 4 over n pi. For n odd. So our solution u of xt is just 4 over pi. And then we have the first few terms are e to the, when n equals 1, e to the minus pi squared t sine pi x. When n is 3, we get 1/3 e to the minus 3 pi squared t sine of 3 pi x plus 1/5 e to the minus 5 pi squared t sine 5 pi x, and so on. If you let x equal 0, all these signs are 0, we get 0. And if you let x equal 1 for all t, these are just signs of multiples of pi. These are all 0. So this satisfies the boundary conditions. And if you let t equal 0, u of x 0 is just, when t is 0, this is just 4 over pi sine pi x and so forth. That's equal to x. This is the Fourier series for x. So everything works out beautifully. So you asked about problems 3 and 4, and those are the solutions.
And the last one for me, page 25, and exercise number 5.
Page 25 in what book?
No, the same homework. No, this is the login. Yeah, login. Yeah, login.
In Logan, the homework for today was just the problems in section 1.1.
Oh, okay.
Okay, and I'm going to go over them. I mean, these are really just problems to develop mathematical technique. Okay, so good. So section 1.1 is really just, so this is Logan, chapter 1, section 1, 1.1. And this is really just introductory information, well, really background, some background about partial differential equations. And the language in Logan is very much the language of physics and engineering, but the mathematics is always the same. So I had assigned problems 1 to 10, and I think I'm going to spend today just going over them, seeing how they go. So let me just find my book. Okay. So problem 1 asks for a solution of what is called the heat equation. I mean, there are sort of 3 fundamental equations that we study: the heat equation, the wave equation, and Laplace's equation. And the heat equation is our equation U sub t, and the constant alpha squared we're writing here in this book is k times U sub xx. By the way, what kind of equation is this? Remember, we had a classification. If you have, let's say I'm using x and y as my variables. If I have a u xx plus b u xy plus c u y plus lower order terms equals something, if you look at b squared minus 4ac, depending on whether this is positive, negative, or 0, we have a classification of partial differential equations. If this is 0, the equation is called parabolic. If it's less than 0, it's called elliptic. If it's greater than 0, it's called hyperbolic. So what type of equation is the wave equation? So you can think of it like this. We have k uxx plus, I'll use t for the variable, plus 0 times uxt, because there's no partial with respect to x and t, plus 0 times utt. Then we have a minus u sub t and some other stuff equals 0. So this is my a, this is my b, this is my c. B squared minus 4ac is 0. So this equation is a parabolic equation. If we take Laplace's equation, which we will study a lot later, that's the equation uxx plus uyy equals 0. The mixed partial uxy doesn't appear, or equivalently, it appears, but with a coefficient of 0. So my a is equal to 1, my b is equal to 0, my c is equal to 1, b squared minus 4ac is minus 4. So this Laplace's equation is a hyperbolic equation. Okay, in any case, this is the heat equation. And problem number 1 is to show that on the domain x going from minus infinity to plus infinity, and t greater than 0, u of xt equals 1 over square root of 4 pi kt e to the minus x squared over 4 kt is a solution. So that's what we have to prove, which means we have to just do some differentiation. If we take the partial of u with respect to x, when you differentiate with respect to x, you get 1 over the square root of 4 pi kt, because this doesn't depend on x. The derivative of this exponent is minus 2x over 4 kt times e to the minus x squared over 4 kt. This is u. So this is minus 2x over 4 kt times u. Okay? Then we have to differentiate again. So the derivative of the first expression is, so this is like, I should write this as minus 2 over 4 is always 2, minus 1 over 2 kt times x times u. So when I differentiate with respect to x, I get minus 1 over 2 kt times u, minus 1 over 2 kt times x times the derivative of u, which gives me another minus x over 2 kt times u. So I get minus 1 over 2 kt u plus x squared over 2 kt squared times u, which if I did this right, no reason to think that I did, but this is minus 1 over 2 kt plus x over 2 kt all squared times u. So I hope you're following along and checking what I'm doing. Just make sure I don't make too many mistakes along the way. Okay. So let me differentiate with respect to t. So u of xt is 1 over the square root of 4 pi k. That's 2 times the square root of pi k times 1 over the square root of t, t to the minus 1/2, e to the minus x squared over 4 kt. So if I differentiate with respect to t, I get minus 1/2 t to the minus 3/2, 1 over 2 times the square root of pi k, e to the minus x squared over 4 kt, plus 1 over 2 root pi k, t to the minus 1/2 times the derivative of this. If I differentiate this exponent, I get minus x squared over 4k. The derivative of 1 over t is minus 1 over t squared times e to the minus x squared over 4 kt. So what is that? This is, so my function u was e to the minus x squared over 4 kt times 1 over the square root of 4 pi kt. So And here, let me try and do this nicely. So this first term is, I have, let me just factor out an e to the minus x squared over 4kt from everything. So what I have over here is 1 over the square root of 4 pi k. This is minus a half t to the minus 3 halves. So that's, I can square root of t times t times minus 1 over 2t. I believe that is correct. And here I have 1 over the square root of 4 pi kt, that's this and this, times this, which is x squared over 4k t squared. And that's what I have. So this is equal to, this times this is u. This is u times minus 1 over 2t plus, let's see, this would be x over 2kt all squared, but I put an extra k in the denominator times a k there. So k uxx is k times this. So that's minus 1 over 2t plus k times x over 2kt all squared times u. And that's exactly what this is u sub t. So I'm always surprised when I manage to get these things right the first time. But that's the first part of the problem. Here's a certain function. Show that it's a solution of the heat equation. And then the next part says for k equals 0.5, use software to sketch several time snapshots on the same set of coordinate axes. So we're going to let k be equal to a half. And I want to write down, I want to graph what the solution of this equation looks like. So let me see if I can go back to screen sharing. And that's my screen share. Okay. So here I have a function, u. Let's see if I can do this. X comma t is going to get mapped to, and what is u of xt? It's 1 over the square root of 4 times pi times k, which is 0.5, times t, times e, so exp is e in maple, e to the power minus x squared over 4 times k, which is 0.5, times t. So that's maybe just because it'll look better Because we know that 4 times a half is 2. Let me just write this as 2. So it doesn't look so complicated. 4 times a half is 2. There we are. So that's what our solution to this heat equation looks like. And we're asked to sketch several time snapshots to see how this evolves in time. So suppose I, for example, I let t equal to 1. And then I want to plot, let's see if this works, u of x comma t. So that's, actually, I could have just said that's u of x1. So at time 1, if you look at the heat distribution in this rod, that's what it looks like. And at t equal 2, looks like that. At t equal 3, I mean, these are all bell-shaped curves. And let's try something more interesting. Let's see if I can plot 3D. U of xt, x goes from, let's say, -5 to 5, and t goes from 0.1 to 10. Wow, okay. So, all right. I mean, this is, if you've taken math, if you took first year calculus at Lehman, you have to take a math lab. If you're lucky, you learned it with Maple. Here is a very simple command, just for 3D math. This is the solution of this heat equation. And if you've never seen something like this, this is really kind of exciting. So remember what our situation is. We have some distribution of heat in this initial distribution of heat in the rod, but the ends are fixed at 0. The temperature at the ends are 0. And what happens with time? So the ends are like here and here. And initially, there's some distribution of temperature. As time evolves, the rod cools down, and it's going to approach asymptotically constant function 0. That's the asymptotic limit. Suppose instead of going from t equal up to just for 10 seconds, I go for 100. You see how flat this is? By the time you're up at t equal 100, this is never a constant line 0, but asymptotically, it's getting closer and closer and closer. And it really is kind of interesting to see. Sketch the solution. Oh, so in the text, they ask you to sketch it in the particular case where x goes from -4 to 4, and the time goes from 0.1 to 4. Yeah, that's what it looks like. And you can experiment. How does changing the coefficient k change the solution? So back when I defined the equation, here it was. Maybe I should have left it in terms of k. It was really 1 over 4 pi k times t over minus x squared over 4 times k times t. That was the general solution. And when I let k equal to a half, everything stayed the same, right? We got exactly the same pictures. Suppose instead of k being a half, suppose we let k equal 10. So here's with k equal to a half. When I let k equal 10, it looks like that. So this is k equal a half. Now with k equal 10, it looks like that. Suppose I let k be equal to 0.1 instead of 0.5. Oh, these are much more, this is really spiky. You have a lot of the mass, a lot of the heat concentrated in the center. So it takes a while, it's going to take longer for it to cool down. All right. Okay, stop share. So I don't know how many of you, if anyone, has Maple. I suggested you get it because you can get it for free from the, as a CUNY student, you get it for free. You don't have to pay for it. And it is worth learning how to use it in differential equations a little bit. Any questions about that? Anyone try to graph any of these solutions in with a computer?
I tried it in Mathematica, but I couldn't get it to work.
So, so among the people I know, they're divided into two groups: the people who use Maple and the people who use Mathematica. And each tries to tell the other that his choice is better. And usually the people who know Maple don't know Mathematica, and the people who know Mathematica don't know Maple. As far as I can tell, they're both great programs, and whatever you can do in one, you can do in the other. Because we use Maple at Lehman, that's all that I ever use. And you can see it's completely trivial to get these graphs in Maple. And I assume it should be as easy to do it in Mathematica, but I just have no experience with that. Okay.
Professor,
Yes.
for problem with ordinary differential equations,
Yes.
it's just one independent variable, right?
Correct.
For partials, you can get more than one independent variable.
You must have more than one. That's the definition. One independent variable is ordinary differential equation. Two or more is partial differential equation. Because when you have two or more, you take partial derivatives. Okay. Problem number 2 is Laplace's equation, which is second partial with respect to x plus the second partial with respect to y equals 0. So as I said at the very beginning, Laplace's equation, uxx plus, uxx plus uyy equals 0, b squared minus 4ac is negative. This is a hyperbolic equation. And we're not really going to, I mean, in one semester, we can do only an infinitesimally small part of the subject of partial differential equations. But there are fundamental differences between parabolic equations, hyperbolic equations, and elliptic equations. And each is a separate study in their own right. So in this case, we take the function u of xy equal to the log. The book writes ln, but I always write log because, you know, once you've taken calculus, forever after, the only log is the natural log. Square root of x squared plus y squared. We want to show that's a solution. It's slightly easier if you just notice that x squared plus y squared, square root is x squared plus y squared to the 1/2. So this is 1/2 the log of x squared plus y squared. So if you differentiate with respect to x, you get 1/2 1 over x squared plus y squared times the derivative of x squared plus y squared with respect to x, which is 2x. So this is x over x squared plus y squared. And if you differentiate again, you get x squared plus y squared squared in the denominator, the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. So this is x squared plus y squared squared. X squared plus y squared minus 2x squared is minus x squared plus y squared. And what is the second partial with respect to y? By just the symmetry of this, you just interchange x and y. You get minus y squared plus x squared over x squared plus y squared squared. So if you take the second partial with respect to x plus the second partial with respect to y, that's minus x squared plus y squared over that plus minus y squared plus x squared over that, and these cancel and you get 0. So that's what it is.
Professor, also, we just using only linear partials, no non-linear partials.
Well, we will look at some nonlinear partial differential equations, but most of what one studies in the beginning means a number of years of this, is linear partial differential equations. Right. Okay. Problem 3 is find the general solution of the equation. Take a function u of x and y. The mixed partial is 0. So what do you think the solution should be? So we start with the function u, we differentiate with respect to y, and then we take that and we differentiate with respect to x. Okay. Suppose we let the partial of u with respect to y, let's call that v. So then this equation says that v sub x So if we're looking for continuous, if we're only considering functions, we're looking at functions which have continuous first and second partial derivatives. So the partial with respect to x is the same as the partial with respect to y. Usually when you write u, x, y, that means differentiate first with respect to x and then with respect to y. So let me stay with that convention. So we take x, differentiate u with respect to x, and then differentiate with respect to y. And let's let the partial of u with respect to x be equal to v. So then the partial of v with respect to y, which is v sub y, this is the partial with respect to y of u sub x, that's uxy. That's what the notation means. This is 0. So what does it mean to say the partial of v with respect to y is 0? It means v is constant with respect to y, which means v is some function of x. Right? If v is a function of x, the partial of v with respect to y is 0. And then we're told that the partial of u with respect to x, that's u sub x, that's equal to v, which is g1 of x, which means u is equal to the integral of g1 of x plus a constant, but the constant is going to be a function of y, I believe. Some function of y. And of course, this is just the function of x, so maybe I should have called this g tilde, g1 of x plus g2 of y. So what we just proved is that if the second partial of u with respect to x and y is 0, then u is the sum of two functions. So u of x and y is a function of x plus a function of y. If we differentiate with respect to x, this is 0. We get the derivative of this, and then we differentiate with respect to y, and we get 0. So the general solution of this partial differential equation, I mean, it is a partial differential equation, is a function of x plus a function of y. So the problem was find the general solution in terms of two arbitrary functions. And fortunately, we just did. Any questions about that? That's kind of a nice little calculus problem. Let's look at number 4. So this is what page? Page 5. Okay. Remember, we saw Laplace's equation. Uxx plus uyy equals 0. And we found a solution that was, well, like log of x squared plus y squared. But now we have a different equation. In this problem, we take the second partial of x and square it, the second partial of y and square it, and the sum is equal to 0. So we want to find the general solution of this differential equation. And we're told that the general solution, so we want to prove that the general solution of this equation is u of xy equals axy plus bx plus cy plus d. A linear, something linear in x and y plus this mixed term. Any suggestions about how to proceed? So let's see, we're only looking at real valued functions of real variables. There's no complex analysis in anything that we're doing. So if the sum of two numbers squared is 0, both of these numbers have to be positive. So uxx and uyy have to equal 0. Because if either of them was positive for any value at all, we'd have a positive number there. So what does it mean to say, so let's solve the equation uxx equals 0. This means, suppose we let v be the partial of u with respect to x. Then if we differentiate v with respect to x, that's the derivative of u with respect to x twice, and that's 0. So this says that the partial of v with respect to x is 0, so that it can only happen is if v is a function of y. Partial of u with respect to x. So the partial of u with respect to x is g of y, which means that u is the integral of g of y dx, which is g of y, the integral of 1 dx, which is g of y plus times the integral of 1 is x plus a constant. Well, let's see. So u is g of y times x plus a constant. Let's see, what is the partial of u with respect to y? It's x times g prime of y. Sorry. Let me just go back and repeat what we've been doing so it'll be clearer to me, certainly to you. We have this differential equation. It's a sum of squares. The only time the sum of squares of two numbers is 0 is if both numbers are 0. So that means if we differentiate u with respect to x twice, it's always 0. If we differentiate u with respect to y twice, it's always 0. So let's disentangle this. So how do we find uxx equals 0? What equations have the property that the second derivative is 0? Let's remember calculus. Suppose we just had a function of one variable. If du dx is 0, then if dv dx is 0, then v is a constant. And sorry, if du, yes. And if du let me say this a little bit more clearly. So suppose we have calculus. We have u as some function of x. And suppose that the second derivative is 0, right? That's what we have here for a partial derivative. The second derivative is 0. That means if we differentiate dy dx, we get 0, which means dy dx is a constant. And if dy dx is a constant, that means y is a constant times x plus d. So y has to be a linear function. If you have a function of one variable and the second derivative is 0, it must be linear, right? That's the only possibility. Now, we have something more complicated. We have some function u of x and y. And the first thing we're told is that if we differentiate u twice with respect to x, we get 0. So that means that the partial with respect to x of the partial with respect to x is 0, which means the partial of u with respect to x has to be constant with respect to x. It's some function of y. And if the partial of u with respect to x is this function of y, that means when you differentiate u, you get g of y. So u of xy has to be equal to x times g of y plus maybe some other function of y, h of y. I'll just leave it like that. Because if you differentiate this twice with respect to x, you get 0. So u of xy is of this form. Now, if you differentiate u with respect to y, you get x g prime of y plus h prime of y. And if you differentiate this a second time, that's the second partial of u with respect to y twice. You differentiate this again, you get x g double prime of y plus h double prime of y. And this is 0 for all x, which means these both have to be 0. Which means g prime of y is some linear function in y, ay plus b, and h double prime of y is cy plus d. Sorry, g of y and h of y are equal to this. So my function u, which is xg of y plus h of y, is equal to x times g of y, axy plus bx plus cy plus d. And that's what we wanted to prove. So let me just review this again. So this was Calc 1, this first part. You have a function of just one variable. And the differentiated twice, you get 0, which means the derivative of the derivative is 0. If the derivative of a function is 0, it's a constant. So dy dx, this function has to be a constant. But if dy dx is a constant, that means y is cx plus d, is linear. So this is the fact from calculus. If you have a function of one variable and its second derivative is 0, it's a linear function. But we have a function of two variables, x and y. And the first thing we start with is that if you differentiate u with respect to x twice, you get 0. That means the derivative with respect to x of the derivative with respect to x is 0. So this function is constant with respect to x. It can only depend on y. So partial of u with respect to x is a function of y, which means u, if you differentiate it with respect to x, you get g of y. So u is x times g of y plus something which is 0 when you differentiate it with respect to x, another function of y. So this is our first big step. But we also know if you differentiate u with respect to y twice, you also get 0. If you take this function, you differentiate it with respect to y, you get xg prime of y plus h prime of y. If you differentiate it again with respect to y, you get x times the second derivative with respect to y plus the second derivative h double prime with respect to y. You get these second derivatives. And this is always 0. So if x times this plus this is always 0, these two things have to be identically 0. If g double prime of y were different from 0 for some y, then as you vary x, this will change, but this won't. That's not possible. So this has to be always 0, which means this has to be always 0. And these are functions of a single variable. So each of them, if the second derivative is 0, must be linear. And this immediately gives our result. Okay. So that's a nice calculus problem. I like that one. Any questions about this?
Professor, the final deduction you did, those constants, um, because my confusion is when you do the process on ordinary, we're getting constants and coefficients, right?
Correct.
So in partial, we got two independent variables,
Correct.
two separate functions. So you then how do you interpret your final coefficients you got in U? You got a x y plus bx.
Right.
Those constants.
So on the previous page,
Mhm.
this was the important observation. V is a function of x and y. And you differentiate it with respect to x and you get 0. If this were just a function of x, this would mean that v is a constant. But v is a function of x and y. So what this means is v is something which doesn't depend on x. It can only depend on y. So instead of this implying that v equals a constant, it implies that v equals some function of y. That's the idea, and that's what's going on. Okay. Now let's keep going. These are fun. Problem number 5. Find the function u of x and t that satisfies the differential equation second partial of u with respect to x is 0 for x between 0 and 1 and t positive, and satisfies the boundary conditions. So if x is between 0 and 1, the boundary conditions will be at x equals 0 and x equal 1. So u when x equals 0 for all time is given by t squared, and at the other end, x equal 1, u of t is equal to 1 for t greater than 0. Okay, so we have something, and at this end, the value of u is 1. Here it's 0 and it's increasing. 0 is like going up like t squared. So we want to find a function that satisfies all of this. So again, uxx equals 0. That's the partial with respect to x of the partial of u with respect to x equals 0, means the partial of u with respect to x, this function, when you differentiate with respect to x is 0 and for all x, it means it only depends on y, it's some function of y. Which means u is x times g of y plus h of y. Oops, yeah, sorry. Not y, t is the variable we're using. So the partial of u with respect to x is just a function of t, and u is g of xg of t plus h of t. Because if you take this function, you differentiate it twice with respect to x, you get 0. U of 0t, when x is 0, this is h of t. And that's t squared. So h of t is t squared. U of 1t is 1 times g of t plus h of t, which is t squared. And that's always equal to 1. So g of t is equal to 1 minus t squared. So u of xt is the function t squared x plus 1 minus t squared. Or 1 plus x minus 1 t squared. So this just C. If you differentiate this twice with respect to x, you get 0. If you plug in x equal to 0, oops, something's not right. Let me just double check what I did. So xg of t plus h of t. When x is 0, this is h of t. And when x is 0, it's t squared. So h of t is t squared. So, oops, I'm sorry. So, and g of t is 1 minus t squared. So everything was right except when I just plugged it into the final answer. So this is x times g of t, x times 1 minus t squared plus h of t plus t squared. Well, that's what it is. Or if you can rearrange it if you like. This is t squared times 1 minus x plus x. In any case, when you let x equal 0, you get t squared. When you let x equal to 1, you get 1. So that's the answer. Questions about this?
Um, so X means space, and T is time, right? So
Well, that's a standard interpretation, yes.
So the final expression, this is referred to eigenvectors and eigenvalues because
No?
mhm, it's not because you got a second a quadratic expression. So I learned in Cat 3 about eigenvalues and eigenvectors. Is related to orthogonality. Yeah, the dot product equal to 0.
Yeah, but it's not here. That's not involved in this problem at all.
Oh, okay.
I mean,
Okay,
never
because
used those words and I never needed to.
yeah, you got a quadratic equation. I mean, it's all right, right? Okay, thanks, Professor.
All right, well, let's try the next problem. Number 6. So we already mentioned the heat equation, which was parabolic, and Laplace's equation, which is hyperbolic. And the third great partial differential equation in physics is the wave equation, which is usually written second partial of u with respect to t is some constant positive uxx. Notice if you write this as, let's say, c squared uxx minus utt equals 0, in that b squared minus 4ac, b is 0, that's this middle term, a is c squared, c is 1, so b squared minus 4ac is minus 4c squared. It's negative, which means this is a elliptic equation. Laplace's equation is hyperbolic, the wave equation is elliptic, and the heat equation or the diffusion equation is parabolic. So we want to verify that if g is any function of one variable, u of xt equals 1 over 2c, the integral from x minus ct to x plus ct, g of s ds, is a solution of the wave equation. And it gives us a hint, which is to use Laplace's rule for differentiating an integral. And rather than just use it as something which comes from the sky, let's figure out from calculus 1 . how we get this. Remember that the fundamental theorem of calculus, in one of its forms, says if you have a function f of x equal to the integral from a to x of f of t dt, then f prime of x is little f evaluated at x. This is the fundamental theorem of calculus, one of its two forms. Let me use u as my variable. F of u is integral from a to u of f of t dt. So f prime of u is f of u. Okay. Suppose we have a function which is the integral from a to some function, let's say phi of x of f of t dt. And I want to find the derivative with respect to x of this. So I can think of this as a composite function. If I have f of u is equal to this, then f of phi of x is the integral from a to phi of x, f of t dt. So this is really, I'm differentiating this composite function. And we use the chain rule. This is f prime of phi of x, phi prime of x. Well, f prime of u is this function evaluated at u. So this is phi of, sorry, this is f of phi of u times phi prime of x. Sorry, f of phi of x, phi prime of x. So let me put this in the notation that is being used. Suppose I have the integral from 0 to some function b of t, f of s ds, and I want to differentiate that with respect to t. So by what we just said, this is capital F. I'm sorry, the notation I used a moment ago was the calculus 1 standard notation, but now I just want to follow the notation that is being used in this exercise. This is the function capital F evaluated at b of t times b prime of t. That's just the chain rule from Calc 1 and the fundamental theorem of calculus in Calc 1. Now, what we actually have in the book is we want to differentiate the integral from a of t to b of t, f of s ds, which you can write as the integral from a of t to 0, f of s ds, plus the integral from 0 to b of t, f of s ds, which I can write as the integral from 0 to b of t, f of s ds, minus, if I reverse the order of integration, the limits of integration, the integral from 0 to a of t, f of s ds. This is f of b of t, b prime of t, minus f of a of t, a prime of t. So this is the formula that you find in the exercise, which is called Leibniz's rule. Okay. Any questions about this? So let's go back now and do the exercise. So this is exercise 6. We have the wave equation. Second partial with respect to t is c squared, second partial with respect to x. And we want to show that for any continuously differentiable function g, a solution is u of xt equal to 1 over 2c, the integral from x minus ct to x plus ct, g of s ds. So let's differentiate this with respect to x. So the partial of u with respect to x, that's u sub x, is 1 over 2c. So what does Leibniz's rule say? It's g evaluated at x plus ct minus g times the derivative of x plus ct with respect to x, which is 1, minus g of x minus ct. That's the partial of u with respect to x. And if I differentiate it again with respect to x, I get 1 over 2c partial of g with respect to x at x plus ct minus partial of g with respect to x of x minus ct. What about when I differentiate with respect to t? So differentiating with respect to t of this integral, I get 1 over 2c g of x plus ct times the derivative of x plus ct with respect to t, which is c, minus g of x minus ct times the derivative of x minus ct with respect to c, which is minus c times minus c, which is, factor out the c, cancels the c here, 1/2 g of x plus ct plus g of x minus ct. So minus times minus is plus. And if I differentiate a second time with respect to t, I get 1/2. When I differentiate this with respect to t, I get partial of g of x plus ct with respect to t times c plus partial of g of x minus ct with respect to t times minus c. So I get a minus c. Take the c out front, I get this. So now let's compare these two. This is uxx. This is utt. What's in the square brackets is the same. What's the difference? Here I have 1 over 2c. Here I have C. If I multiply this by C squared, I get a C over 2, and that's exactly what I have here. So it all works. And I do have a solution. Any questions about that? All right, let me just pause for a moment because I like to take attendance every now and then. I have Miawi, Buzanuli, Gafour, Cabrera, Krylenko, Chavez, Yapur, Lee, De Leon, Polenko. Yep, that's it. Okay. Any questions about any of this?
The wave equation, you already explained 3 category of equation. My question is, it belongs to, I mean, when you classify those equations, the wave, the heat, and the third one, it's a family, it's a family of equations based on the graph, or just is a model for the physics? Because those equations from physics.
Oh, I'm not sure what you're asking. So these are 3 equations that are extremely important in physics.
Okay.
And as it turns out, they are representatives of the 3 types of second order linear partial differential equations, which is what a large chunk of this subject is about. So the heat equation is parabolic, and the wave equation is hyperbolic, and sorry, the Laplace's equation, and the other is elliptic. So in these 3 simple equations, which are infinitely important, you have one example from each of the 3 classes of partial differential equations. So that's the story. Okay. I think that is it for today. And on Wednesday, what I want to talk about is section 1.2 of the Logan book, which is on conservation equations. And the language is perhaps a little bit unusual because it's the language of physics and engineering to a certain extent. But the mathematics is just the same mathematics we do all the time, which is basically advanced calculus. In any case, that's it for today. And I will see you all. Well, I won't see you, of course, but we'll all be back, I hope, on Wednesday. All right. Bye, everybody.
Thank you. Take care.
Bye. Take care.